One more thing about the distributed computing. I already said you could buy the resources, and I just checked at Amazon. They provide computing time on paid basis, or you can even have some free. So I'll give you different ways of working with their computers, and depending on what you want to achieve, you can work here, and you can see that some right here you can't really see this exactly specification, but anyway, that you get some hours for free per month. Here is some kind of Linux Red Hat instance, and you can also use some Windows setup. The other one is you start paying stuff, and you pay some dollars per month, and how much you pay depends on how you specify the computers you need. It could be that your computer has so and so much memory, it has so and so many cores, it has graphic cards, and everything you add on to your specification cost, of course, more. But you can have, usually when you start testing, you can usually have some free time to see what you really need, and then you can work from there on. So going on the lecture slides, one thing that is a big challenge when you start doing larger experiments is to how you should store and organize your data in a clean and efficient way, because sometimes it's the data produced by a sub analysis may be efficient to store in a certain way in those for each case. But when you are trying to put everything together, it would make more sense to have it stored in a completely different way. So the question is how you store the data, and also on how much data it is, of course. So if you're talking about each analysis results in a table, then the question is how you should organize these tables. It could be that you have several small tables or one big table with many columns. So usually it's easier to work with one large file or database. And many of the languages you approached until now, probably, they are designed for in-memory computation. So they're not storing anything unless you really wanted to. But if you start doing parallel and distributed computing or working on many data sets, you have to store the results, intermediate results. So the question is how you can store it efficiently. One way is to put everything in an Excel sheet, but at some point Excel sheets are not really efficient. Then it's probably better to put the data in some kind of text file, which is then analyzed by some kind of script. It could be a Python script, MATLAB, R, whatever. And then from there on, continue. You can also, as I mentioned, instead of putting in text files or some kind of basic database files, you can really use the database service. And that is something you have to decide when you start setting up your system. Another thing is also how you organize the computers. So if you have your own workstation, it's easy. Maybe it's a shared resource. And of course, you have to share it with your colleagues and agree on when it's using it when, who is using it when. But in principle, when you're working in a larger content, you have three players. One is the resources. So that is computers, how much memory it has, how much storage. Also, in some sense, the network availability. And these are limited for you for a limited time. unless you're in a very fortunate case that you have your big computer for yourself. Then the next thing is you have a set of tasks that you want to run. And that is something you can have that needs some kind of resources, and you also may need to specify a little bit about execution time you need. And then, as it is very inefficient if a single person has this power computer, it's usually many users who share it and many who are submitting jobs to these computers. And it's not really efficient for the general, say, user population of that system, that one user takes everything at once and using it for some given time. So usually there is some kind of task swapping. You say you want to achieve the results within some given time, and the system is kind of managing the jobs in a way that everybody gets to the point in a reasonable time. There's also a queue where you put your send in your jobs, and then you have to wait until it's your turn and you get the resources. The resources are probably also distributed according to some institute rules that your group contributed with so and so many nodes on the cluster. Therefore, you can only use that many nodes. You cannot use the whole thing, or if you want to use the whole thing, then you have to apply for more resources and be put in a different task queue. So there are different ways how this is managed, and the exact rules at ETH you probably have to look up in the computing infrastructure department on their web pages, how it works to access the clusters. I actually don't know how it works. When we're talking about a cluster, we have a structure where you have a master or main node. Oops, one tool. So, no, wait. So you have a main node, or maybe several. So that would be the main. And then you have worker nodes, many. And they are interconnected. They are sharing resources, like you have a couple of disks that they access and go to. And from the main node, you distribute all the tasks in according to different strategies, depending on how your task is, how your job is built up. And the worker node are doing the job and sending back the results, or telling, I'm done. The results are stored here. And then you can use the main node again to retrieve the data that came out. Within the main node, which is the one you actually log into as a user, there is also a scheduler, or somewhere there is a scheduler running around that tells who gets what time and what the resources they can have. And that's the machine that tries to make a fair distribution of the computational resources. Yeah, and depending on the architecture, you may have different entry points in this, and this one may only access this fraction. This may take the whole thing. It depends a little bit on the architecture of the cluster, but this is something you can read about on the pages for the cluster service. The results that I talked about, they are stored in either in text files, but if it gets more, it's sometimes actually makes sense to use a database. We have until now used data frames using pandas. The pandas data frames are at least were designed to work only in memory locally, but there are data frames that actually also can work on distributed data and data on disk. So it's more like a database interface. What you typically have is you have different tables within this database. So for example, you have one table about the individuals, describing each individual in the experiment. But this information you don't have to bring in the big table of measurements, for example. So then you can just have an index saying this measurement relates to that individual. And next measurement relates to another individual, and so on. And then you can make a cross-linking with this database, and that's why it's also called relational database. And here you can see that here you have the animals, 1, 2, 3, and you can see here that it refers to animal 1 has apparently cancer, some anisotropy measurement is 0.5, and the volume is 1. And then you can see the different measurements in this table. Yeah, so you can use this way of connecting different informations in the tables. So it's a pretty efficient way of storing measurement data. SQL, or actually SQL is how it's pronounced, is a very old language actually. It dates back to, I think, even to the 70s at least. It's a language that is used to query information in databases. So you can use it for searching information, called querying. It can also be used to add new information into the database, and that's called an inserting. So there are different ways you can use, there are different actually database servers, and also in some cases you can have some local servers, and depending on what you are working with, the service is provided in different ways. There are in Python also SQL connection if you want to use that. There are even a link where you can drag information out from the SQL database into a pandas data frame and work with that. Depends a little bit on what you want to achieve. In principle, both can be used in parallel, or you can use them as a mix. Exactly what you're using is probably a matter of taste, or preference, what you want to do and what you need to do. But I would say it's in principle, as when you need to have the data the data is so large that you can't access it, put everything in memory, then you probably will at least use the SQL service to store the data. If you then use the SQL to do all the queries, or if you do a data frame for the queries, that is more question what you prefer to do. Some basic programming using SQL is you do select a column. So when you do a query, you do select volume from the table cells. And then you get this list out. Or else you can also do the query, get the average volume. Then it actually computes the average already from this query. So then you to select average volume from cells where the type is cancer. And then you get that average value. So this can be done from any tool that can work with SQL. I think there is even a connection to Excel if you want to use that. Or in Word, there is also, I think you can get, for example, you can use SQL as address database in Word if you like to do that. But you can also do this using scripting with Python and so on. The other way would be that you, for example, extract a couple of columns from the SQL database and read it directly into a data frame. And from there on, you do some more dedicated work based on the data frames, because the data frames, you have the advantage that you can also easily do plotting in the same framework as you have seen already. So actually, my personal preference is as soon as possible leave SQL, but that's my personal choice. Then you can go into more complicated things, and you probably can see that these kind of queries is something you can do the same also if you want to do work with the pandas. So here is an example where you select a volume from the cells table, where the animals are selected based on the weight. So then we actually take in information you do a selection of weights in the table, and let's see, yeah, no. Here. So you can do a selection that the weight must be more than 40. Then we get the animals 1 and 3, and then we check here, make the selection in this table based on animal 1 and 3, and then we check how big the average is, or how much the average is. I think it was, no, I just want to get the volume. Okay. And then we can also go even more complicated. So you can always write longer and longer lines in this language about joining different tables and combining them. There are even classes dedicated to database programming. So if you want or need this, you really have to go to that material. Then there are also tasks, other alternatives. So there's something called no SQL, but it can look like in the beginning that it's very easy to make the requests from SQL, but it gets, as you also saw in the later examples, that it can be really complicated after a while. So then you can use other network, you can do some network analysis. So for example, here, how many cells there are within 2 connections of each cell. So then we have to do some kind of counting on different cells, and then we have to join different networks and check how they are. But it's getting more and more complicated to get these things together. And so NoSQL is actually not meaning no SQL, but not only. So that is a new generation of database handling, and it's also more efficient for large-scale analysis. And one is called MongoDB, and it's really dedicated for network analysis or graph analysis, and they are actually called graph databases. So if you really go big data, maybe SQL, the original definition of SQL is maybe not the right thing, but you should probably look at other alternatives. Now, big data is a word that you probably have heard a lot of already in this class, but also in media, in different classes. It is, some people define big data as when you can't fit the data within a rack in a server station, then you are talking big data. So that would be probably several petabytes or something. Then you were talking about big data. But in our case, we may not reach the petabytes, but still we have large amounts of data, and how it's produced, it's we need to think about, we have velocities, we have volumes, and we have varieties that we have to work with in our images. And then when we have a large heterogeneity in the data, we need to really make sure that the analysis has good performance. It should also be scalable. So what you do for a single object should also work for 1,000. And that should be possible to do flexibly. Also, if you would realize after a while that that analysis wasn't the right one, there are some biases in the measurements that you need to correct for. And you also need to add some flexibility, that it's easy to take out one piece that is maybe not performing in the way you thought, and then easily rerun it without rewriting the whole managing framework and everything. Scaling up shouldn't be too scary. I mean, analyzing 10 images or 100 or 1,000 should be more or less the same effort for you. But the computer has to work a lot longer. Or if you add more nodes, of course, you can do it quicker, but you shouldn't have to worry that you have much data. Only that it takes more time for the computer to deliver the results, but your work shouldn't be much different if you have planned it well. Another thing is a problem with big data is when you're starving for enough data. So that is also a question. That the data is, you always need more data. I mean, if for doing machine learning, to do machine learning good, you need a lot of data. You need a lot of training data in order to build up models that are reliable. And a very important thing, which actually goes back to this when scaling isn't scary, you should develop some code that where everything is automated. So the only human interaction should be at the starting point when you say, okay, run this with this set of parameters. And then let the computer retire for a while, or do its work, and afterwards it comes out. If you need to click during the process, then you're lost. In particular, if you have large data sets. Okay, you can click a little bit if you have 10 images. Okay, takes time, it's not fun. If you have 100, I don't believe it's so much fun anymore. And if you even increase it 1,000, it's not even realistic to start clicking around in the images. So you really have to make sure that the code is reliably automated, so you don't have to interact with the data during the processing. A way to handle the big data problems is a Google story that they had the problem that they wanted to analyze the quality of different pages. And they use a page quality algorithm called Pagerank. It's commercial code, and we don't know it exactly how it works. But they need to run this Pagerank on every page they want to look at in the network, in their search engines. So what they need to do is to run for every site on the internet, that's a many, compare the rank with the current site that you're at. And then, of course, this looks like a very big parallel task. So you just divide all the web pages out on the web and assign each block to each computer. That is trivial for parallelization. It's only, the problem is it takes too long, because every site needs to be compared to every site. And that's not really feasible. So the complexity is actually n squared. And that takes very, very long time. You can probably compute one loop on a really fast computer, really big computer, it would take still months for one indexing, and they want indexing all the time. And you could try to divide it into languages, because among English language sites, they usually keep within themselves. The Chinese sites keep it within themselves, and then you could run the PageRank index on them separately. But all of a sudden, there is a link between the English site and the Chinese site, and then all of a sudden you're lost, because then you start again to look into what the neighbor is doing, and you have to look into the indices that you get from that, and then it's not a good idea anymore. Then in this computation, what happens if one computer or hard drive crashes? It happens, definitely. Do we have a backup computer that replaces it? So that would be very expensive. A backup computer for every single system is not feasible. But that would be maybe okay with a few computers, but with hundreds and thousands of computers, no. Maybe there's the problem that there was an earthquake and all the computers go down. So then you have to rely on having a distributed system where everybody are doing a little bit of every task all over the distributed places. What PageRank isn't just doing is not only counting how many links there are, but it's also looking for old rankings on the same page. So you need to run the PageRank many times until the rank is converging for a page. So it's really a very large task to handle. What Google did was to come up with something called Mapreduce. That's a kind of a strategy how you work with the data. And it's divided into two parts. One is you have a mapping. So for example, the mapping would be that you have an input data vector, which contains some numbers. You have a mapping, so a function that converts it to something else. In this case, just x squared. So the mapping of f, using f on the data set L, gives you the squared sequence instead. Reduce is something that's a little bit more complicated, but it's actually bunching elements of the data together somehow. So one example would be to sum the data within the sequence. And we have the reduction function with two entries, G, A, and B, which is the same as A plus B. Now we can call the reduce function as a sequence like this, where we have first G1, 2, and then we call it with a 3, call that with a 4, call that with a 5. Then we would have the sum in the end. A more efficient way would probably split it down, doing operations in a cascade. So it's kind of a tree-like processing. Then you would compute sub-fractions, and then you can actually, with doing this, you can split the task, the reduction task, on many more nodes. So you could in principle assign the task of these two to each one node, and then the last ones actually, you need to call on a single node. So there is kind of a convergence point where you have to do a lot. So that can be split down in different strategies, and that's also the task of the scheduler to optimize this splitting. No, reduction, sorry. So a typical Mapreduce work is to first partition the data into small chunks on all machines in a cluster. Then you do some mapping on each element. That could be, for example, computing some PageRank. Then you have to reshuffle and reposition or group the data in different ways. And finally, you have to reduce it to get the final result and then write it to disk. So typically a job in the Mapreduce framework is that you have a data set, you have a mapping function, and you have a reduction function. And that is what you send out to be done. Then you can also work with key value pairs or grouping. So a principle, a key value pair is that you have an index or something that you can compare. Could be a word, could be a number, could be something. That can be sorted or grouped somehow. And associated with this key, you have some data. Could be a single number, could also be an image, could be, yeah, well, whatever. And that makes it also, this is also a way how you can sort and efficiently work with the data. And that can also be then distributed in a good way. So let's look at an example using the Mapreduce. So we have some kind of folder full of text documents. So we have a lot of lines in this. And the first mapping would be that we split the lines into words. So we get some kind of a list of only words, and then we can group them defined as keys. Then reduction adds up the values of each word. So in this case, we have one line of cat, dog, car, and the next line we have dog, car, dog. And the mapping here says that we have cat, dog, and cat is the key, and then we have the value 1. And then we do some reshuffling or regrouping, and we can see that cat has only 1, and the dog is a list of 3 elements, and the car is a list of 2 elements. And finally, we do a reduction where we actually sum up the results of each table here. And we see that the cat has 1 count, the dog has 3 counts, and the car has 2 counts. So that would be a workflow for doing the Mapreduce. That can be applied, for example, on Shakespeare's A Midsummer Night's Dream, which is loaded here. We can see that there is a lot of lines. I don't see everything. It's just looking at the first 5 lines in this case. And then we start running some analysis of that. And here we need to run some kind of analysis. So what it's doing is first it's doing some kind of lowercase conversion. We strip it up and we split. And then we get our words, and then we can get them into a table and starting doing some word counting. And that is a pretty quick thing. It can just be run like this. And the output of this is afterwards that we get the most frequent words. And this is probably not very surprising that these words come up on the top. But the least frequent words are pretty strange words, not so much used. And there you can see these are the 10 least frequent words, and they only used once in the whole text. Another one is also using, so here we have write the line to words function as a function instead. In principle, what we get is when we give it a line, it gives the output a list of words instead. And here is a little test. So this is an inline unit test that checks that it actually provides what it's supposed to. Now we want to take this over to doing image processing and more practical work. And for that, we use a package called DAG. And in DAG, we have bags. So that's all the units of work that we want to execute. And in a DAG bag, we have a map, we have a filter, folding, and also you can do some grouping. And the idea is that with a DAG bag, you can split up the data in parallel and telling how many cores or machines should execute. And it's also working with a lazy processing. So it's not only executing the code if it's needed. And it can even work well if the data is larger than the memory itself. So it gets the data as it's needed. For that, we need to do some coding. So first we need to import the task bag. And then we have some line here where we call all the from the sequence. So this is all the lines from the Midsummer Night's Dream. We tell that the partitions should be 10,000 elements. And then we get some line bag here. Then we want to say, we want to create some kind of mapping. Then we use our line to words function and then it's flattening it. And we see that we got 13 partitions based on the size here. And then we can run the reduction and do some frequency count. And here we can get the topmost and the bottommost. So all the code we did before has been reduced into a few lines using this task bag analysis, which is pretty convenient. And also it allows us now to say, okay, this should be run on in parallel. And if we run this analysis, you can see that I already did it, and you can see the output as this list of key value combinations, the, and, I, and so on. On the bottom list, we have key value combinations, Midsummer Nights with some value, Veins, New Bend, and so on. What happens in this processing, you can actually also visualize with the profiler, where you can see that my cores, they're working at different times. In this case, I think I set somewhere to run it on 4 cores. So it's not even using all the cores I have available in this computer. And you can also see how much the memory is used and how much the CPU is used during this processing. So you can really get a graphical visualization how well the parallelization is going. Final thing I'm going to talk about is environments for distributed computing. And there are different environments for this. One is Hadoop. It's an open source version of the Mapreduce, and it was developed by Yahoo and is now also released in the Apache project. It has, in principle, the whole infrastructure with file system, hand storage, and so each machine has the possibility to get the data when it's needed at the right time. Also, the storage is automatically expanded with the processing power, and now it's actually the background, the backbone of how many of these big companies are dealing with the exabytes of data that are produced every day. And another one is Spark. It's another alternative, and it's a general tool that is actually used very popularly for these DAG workflows. It's a kind of coarse-grained. It also does the Mapreduce and join operations, and it's doing a lot of in-memory caching. So you can use it for parallel computing without these different libraries and so on. It's rather declarative than imperative, but anyway, it's actually a bit strange if it's working with DAGs, but anyway. So no, it's declarative. That's right. So I'm mixing up. Sorry. So instead of telling 3 computers to wait for data from computer 2, and it could actually send data, different tasks up to other computers and do them when they're needed. Scheduling is automatic, so you don't have to think about that. And it handles the data results, however you design it to do. So it could be in memory, on disk, could also be done redundantly if you want it. So this is a good framework for working on this. So Dask is a pure Python environment, and in Python there is an environment called Dask, the idea is to bring a fault-tolerant and robust distributed computing infrastructure for the Python code. And it's based also on using NumPy, SciPy, and similar things within this parallel interface. The ideas that I'm showing now, they will be used essentially, they're using Dask, but it could also be using it well in Spark and Hadoop-like problems. So here we have some different DAG. No, DAG is something I actually introduced already in the first lecture, called the directed acyclical graphs. And they can be used in many of these different computing systems for machine learning and also for other numerical processing. To look into more about this, there's a lot of links that you can follow, and yeah, please follow which one you think is useful. And also in TensorFlow, you can even do optimization, seeing which kind of operation is the most efficient one in order to optimize your processing afterwards. And this is an example from Facebook, where they try working with different loop systems. And here we are talking about 2D average pooling, sorry. And then it generates different codes in order to see which one is operating the fastest and the most efficient. And finally, they get to some kind of fastest kernels, and these are the ones that will be used later in the work. So we have come back actually to an example that I started introducing already in the first lecture. Let's create some small images. 5 by 5 is really small. It has zeros and ones, and that results in this little code here. So we only look actually at image 1, which is created. It only has one block. Now, if you want to do some arithmetics with it, you can see that you have image 1 minus 10 plus image 2 times 50, and that is added, and then we produce an image 4. And you can see the graph for this is that some of the work can be done in parallel, and then at some point we have to wait till the results are coming. Then we can do the last adding, and that results in an image. No, something happened here. Some other calculations, a little bit more complicated. We add some image 5 here, which we introduce. Then we can see as image 5 is actually a multiplication of image 1 and image 4. And you can see that here comes 1 in, do the adding, and we have to wait here at this operation until we have got the results from both. So this one is already forwarded, but it has to wait until it gets the results from here. So this one is kind of waiting until getting the result. Now we want to do some image processing using this DAGs. And we have the task. We want to look at different bubble images. So here's a set of images from the plateau border TIFF file. Summing up everything, it looks like this. You can see there are a lot of bubbles, and looking in this overlay, there's a lot of bubbles that we need to do something about. And looking at all the 10 frames that are in the data set, it looks like this. You should see something like lines in about, whoops, like this. So these would be the images. So these are 10 images that we are going to analyze. And you can also look at the data like this. You can see that there are some bubble walls and that you actually can identify several bubbles within this data set. So let's create a DAG for analyzing this foam image. But first we create a foam. So it's a DA foam, and it should be divided into, no, it's actually a little bit divided by 255. And then we create chunks of 20, 400, 400. And we see here that the image is actually 100 by 400, 400. So we have divided this image into 5 chunks. Now, when we execute this, we see that, okay, we have 4 chunks. That's fine. And then we want to add a filter operation to this. And then we want to use the Dask version of SciPy's ND filter, Gaussian filter. And that looks a bit ugly, actually, when you look at this task. And the interesting thing is, when you now look at this, is that when you do filtering on different chunks, there will be overlapping regions. And these overlapping regions, they have to be handled in a good way. So here you can see in the graph that there is some overlap at that each of these, this one needs information from that side and it needs information from that side. And likewise here and here and here, before you can do the final filtering and bring it up and finally produce the image. Then we want to segment the data also and do some erosion. And then we see that the graph is growing even more. So we start here with the Gaussian filtering, which is the code we already saw. And then what we also need to do is to do some segmentation. It happens somewhere around here. That's around here. We do this segmentation. And then we again want to do erosion. And that's again something that has overlap between the blocks. So we need to do some kind of overlap synchronization. And finally, we can get the eroded result. Final step is we want to also apply some labeling. For that, we want to add some labeling code. And that we also add as a map block to our graph. And go on, oops. And that can be processed, and then we see the result. And here we can see that there are different blocks, but you see this banding, and that's something we don't really want to see maybe. The banding is because we have different labels in these regions here. And finally, we want to look at the profile output, and you can see that some things are happening a lot and some things, so we needed to wait a little bit down here. And then there's a lot of things happening in parallel. So this was again set to working with 4 cores, sorry. And you can also see that the CPU and memory, they are going up and down depending on what tasks are done at the moment. So you grow in size when you're doing the different processing, and then you reduce and come back to the final result. Then there is an importance in how you run, which order you execute these tasks. You could do either select a slice and filter it, or you can filter and select a slice afterwards. And that actually gives you different performance times. And you can see here that if we do single slice processing with 4 workers, and you do filtering slices first and then compute something, that you have a different execution time. So it takes much longer to extract first all the slices, then to compute everything in one block. So the result is the same in the end, but depending on how you extract the data, in which order, you can actually have different execution times. So it's really important that you do it in the right way. But that you can probably already see doing some small test experiments, saying, okay, this way is bad, this way is good. And then you go decide the way you want to do. And that probably also depends a little bit on how you do your analysis. So you really have to test and see which is the best way for your particular example. And we can see that in one case, we have a single slice and filter. We only have a very basic graph. If you work with the other one, filter and select slice, then you have a much many more chunks of the image, and all chunks are processed in parallel, and that is where we have our gain. And then you can get the slice from the result. So this was the last topic, actually. Cloud computing is something that I actually already indicated in with this Amazon clustering, is that you can actually buying a computer of your own is maybe good for you. You have it already available, but it's expensive, and usually it's not fully used. There are nights when people are not using it, or maybe there are times in between, and all this time you pay for, even though you're not using it. What you also have to handle is the whole IT handling, that you have to maintain the computer, you have to maintain licenses, you have to make sure that everything is okay. So that costs actually also manpower to have a local computer. If you use cloud resources, you first of all, you can just have an automatic setup. In some cases, you can even design which kind of computer you want to have, and then you pay for the resources you use when you use them. And then you don't have to think about optimizing or managing the computers. They are already there, and they are probably also handled in more efficient way if there is a large-scale computing center. Spark is a platform that is used a lot, and with Spark you can have a lot of typical typical functions, and you can do tools that are built for it. So you already have k-means, you have matrix factorization, different machine learning algorithms, and you can actually win a lot by using these systems based on Spark or something like that. Then there's also a lot of academic support on this. You have a lot of source code available on GitHub. You also have no patents or restrictions on usage. And if you want to check on machine learning, this is actually a line I would have to verify, because this is an old line from my predecessor. But there's probably some kind of machine learning course at ETH, which is based on Spark, using Spark. Yeah, and then some streaming is something you may have to think about. When you have a lot of data coming in all the time, you may have to do some real-time analysis and get results out as they come. That should also be possible to scale, connect to more computers if needed. And then it should also start working on those computers if it gets it, and blow up some like some amoeba going out on using the resources you can have. Another thing is, sometimes you have so much data that you cannot handle it, and sometimes you can just say that you want an approximate result. You don't need the exact, but you need more or less a guiding numbers. You can say, compute the mean volume of this data within 5 minutes or 5 hours or something like that. And then it gives you that estimate, which is within some reasonable tolerance. And that can be enough for you to make your conclusions in a real-time context. So that was a lot of talking, a lot of information, a lot of hints on what you can learn on other places. This just opens up a big field, which I am not able to cover within 2 hours. All of these topics that you see here in this summary, they probably represent more than one course at in computer science and computer engineering at ETH. So there is a lot of material behind the slides in this lecture. I hope you got at least an idea what you can do, but it's not the end of. So if you want to use these possibilities, you probably have to dig deeper and learn more. This was also the last lecture that I'm giving in this class. I hope you enjoyed it. And there is also course evaluation. I think the evaluation is open until the 25th of May. I ask you to fill out this evaluation in order to give me some hints on what I can improve or if you liked it and so on. Yeah, and then in 2 weeks on June 3rd, I think it is, yes, we have some projects that people may want to present, and I'm looking forward to that. Next week, I will be around. If you have questions for your projects, about the course, about your own projects, PhD projects where you may want to have some hints. But otherwise, I thank you all for participating and wish you good luck for the exams. Thank you.